Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is types of redox reactions. So, the different types of redox reaction that we'll be doing is combination reactions, decomposition reaction, displacement reactions, and disproportionation reactions. So, let us begin combination reactions. So a combination reaction can be illustrated as A plus B forms C, where either A or B or both should be in elemental form. All combustion reactions come in this category. So for example, carbon plus oxygen it combines to form carbon dioxide. This is a combination reaction. Similarly, magnesium plus nitrogen forms magnesium nitride. Methane plus oxygen forms carbon dioxide plus water. These are combination reactions. What we see is that these reactions are also redox reaction, where one element undergoes increase in oxidation state, which is oxidation, and the other element undergoes decrease in oxidation state, which is a reduction. So these are combination reactions. In this, magnesium undergoes oxidation, nitrogen undergoes reduction. The oxidation state of carbon increases from -4 to +4, and that of oxygen decreases from 0 to -2. So this is a redox reaction. The second category of redox reactions is decomposition reactions. These are actually reverse of the combination reactions. In these, a compound breaks away into its elements. So a decomposition reaction leads to breakdown of a compound into two or more components, at least one of which must be in the elemental state. For example, water decomposes into hydrogen and oxygen. Sodium hydride decomposes into sodium and hydrogen. Potassium chloride decomposes into potassium chloride and oxygen. Again, we see that one element undergoes decrease in oxidation number while the other undergoes increase in oxidation number. Hydrogen is getting reduced here and oxygen is getting oxidized. Similarly, sodium is getting reduced and hydrogen is getting oxidized. In case of potassium chlorate, chlorine changes its oxidation state from +5 to -1, which is decrease in oxidation state. So it's undergoing reduction, and oxygen is undergoing oxidation. It's losing its electron. There are some reactions where decomposition occurs, but it's not a redox reaction. Calcium carbonate decomposes into calcium oxide and carbon dioxide, but there is no change in oxidation number of any of the elements. So it's not a redox reaction. Not all decomposition reactions are a redox reaction. Third category of reactions is displacement reaction. For example, an element X displaces element Y from its compound. So X plus YZ will form XZ plus Y. Y is displaced. This displacement reaction can be categorized into two categories: metal displacement, where a metal displaces an element from its salt, or non-metal displacement reaction, which we'll take up later. So here zinc displaces copper from its compound, and as a result zinc sulfate is formed. Similarly, calcium displaces vanadium from its salts and calcium oxide is formed. So this kind of metal displacement reactions are used in metallurgical processes, and pure metals are obtained from their compounds using suitable reducing agents. For example, calcium acts as a reducing agent to obtain vanadium, magnesium acts as a reducing agent to obtain titanium, and aluminium acts as a reducing agent to obtain chromium. Now, the substance which acts as a reducing agent is a better reducing agent than one which is being displaced. Second category is non-metal displacement reactions. So, in non-metal displacement reactions, these reactions include hydrogen displacement and a rarely occurring reaction involving oxygen displacement also. All alkali metals and some alkaline earth metals will displace hydrogen from cold water. So alkali metal will take the place of hydrogen and form alkali metal hydroxide, and hydrogen will be released as a result. This is a redox reaction also because sodium undergoes an increase in oxidation number, whereas hydrogen undergoes decrease in oxidation number. Hydrogen gets reduced, sodium gets oxidized. Similarly, calcium will displace hydrogen to form calcium hydroxide. Now, active metals, alkali metals and alkaline earth metals displace hydrogen from cold water. Less active metals such as magnesium and iron will react with steam rather than cold water to produce dihydrogen gas. So magnesium reacts with steam to produce hydrogen gas, and as a result magnesium hydroxide is formed. Iron reacts with water to form iron oxide, and hydrogen gas is displaced. Now, many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. Dihydrogen from acids may even be produced by those metals which do not react with steam. For example, cadmium and tin will react with acids to displace hydrogen. So here are some examples. Zinc reacts with hydrochloric acid to form zinc chloride and hydrogen. Magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen. And iron reacts with hydrochloric acid to produce iron chloride and hydrogen. All these reactions can be used in laboratory to prepare dihydrogen gas. And the rate of evolution of hydrogen gas can tell us which metal is more reactive. For example, this is the fastest reaction out of the three. So magnesium is the most reactive. Iron plus HCl is the slowest reaction. So iron is least reactive metal. And very less active metals, for example, silver and gold, do not react even with hydrochloric acid. So these are non-reactive and they occur in native state in nature. The activity series of halogens can also be synthesized from the rates of reactions, just like we have created activity series of metals. We know magnesium is more reactive than zinc, is more reactive than iron. Similarly, in case of halogens, as oxidizing agent, the power decreases on moving down from fluorine to iodine in group 17 of periodic table. That is, fluorine is the strongest oxidizing agent and it is so reactive that it can replace chlorides, bromides and iodide ions in solution. In fact, it can attack water and displace oxygen of water as well. Water plus fluorine will form HF and oxygen. So for this reason, the displacement reaction of chlorine, bromine and iodine using fluorine are not generally carried out in aqueous solution, because in aqueous solution oxygen is given. Chlorine can displace bromine and iodide ions in aqueous solution. So chlorine is more reactive than bromide and iodide ions. So chlorine will displace bromide ions from KBr, and as a result bromine gas is released. Similarly, chlorine can displace iodide ions and iodine gas will be released. As bromine and iodine are colored and dissolved in carbon tetrachloride, these two reactions can be used in laboratory for detection of these compounds. So the color of the solution will indicate whether bromine or iodine is formed or not. For example, when this reaction is carried out in presence of carbon tetrachloride, the bromine released dissolves in carbon tetrachloride layer and gives reddish brown color to the layer. So, and similarly, in when reaction with iodide is carried out, the violet color in carbon tetrachloride layer above water will show that iodine is being released. So this test is known as layer test, and it's used for identifying bromide ions and iodide ions in the laboratory. Bromine can displace iodide ions also because it's more reactive than iodide. So bromine plus iodide will form bromide ions and iodine. The halogen displacement reactions have direct industrial applications. Fluorine is the strongest oxidizing agent. There is no way to oxidize fluoride ions to fluorine by chemical means because it's the strongest oxidizing agent. So in order to obtain fluorine, we have to oxidize fluoride ions electrolytically. We have to pass electric current through them to oxidize fluoride ions to fluorine gas. Chemical cannot be used in this reaction. Fourth category of reactions is disproportionation reaction. In disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. For example, hydrogen peroxide when decomposes form water and oxygen. So oxygen from -1 oxidation state decreases its oxidation number to -2. This is reduction, and simultaneously it increases its oxidation number from -1 to 0. This is oxidation. So same element oxygen is being oxidized as well as reduced. This kind of reaction is called disproportionation reaction. Similarly, phosphorus in alkaline medium gets oxidized to hypophosphorus acid and reduced to phosphine from 0 to -3 and from 0 to +1. Sulfur gets oxidized to thiosulfate ions and reduced to sulfite ions. Chlorine gets oxidized to hypochlorite ion and reduced to chloride ion. So all these are examples of disproportionation reaction. Bromine and iodine also can carry out these kinds of reactions. But in case of fluorine, we do not get a disproportionation reaction. Fluorine will react with alkaline hydroxide ions to form fluoride ions, oxygen difluoride, and water. The oxidation state can decrease from 0 to -1, but it cannot exist in +1 oxidation state. So this means that it can be reduced, but it cannot be oxidized. Fluorine will attack water to produce some oxygen also. This departure shown by fluorine is due to the fact that it being the most electronegative element cannot exhibit any positive oxidation state. It means that amongst halogens, fluorine will not show disproportionation reaction. So these are the four kinds of redox reactions: combination reaction, decomposition reactions, metal and non-metal displacement reactions, and disproportionation reactions. Using this knowledge, we can solve the following questions. Which of the following does not show disproportionation reaction? So here, hypochlorite ion, the oxidation state of chlorine is +1. In this case, it is +3. In this case, it's +5. And in this case, it's +7. So this is the species which will not undergo disproportionation reaction because it can only be reduced. We cannot oxidize it further. Others can be oxidized as well as reduced simultaneously. Suggest a scheme of classification for following redox reaction. In this case, nitrogen and oxygen combines to form nitric oxide. So this is a combination reaction. In this case, lead nitrate decomposes into lead oxide and nitrogen dioxide and oxygen. This is a decomposition reaction. Here, sodium hydride plus water forms sodium hydroxide, and hydrogen hydride displaces hydrogen from water. So this is a displacement reaction. And in this case, the nitrogen and nitrogen dioxide undergoes simultaneously oxidation as well as reduction. So this is an example of disproportionation reaction. That's all in today's video. If you like the video, please do share and subscribe. Press the like button. Thank you. Have a nice day.